Hello, I'd like to welcome you to the next installment of the Optimus webinar series, using Optimus to get the best value from your simulations. Today we will be presenting and demonstrating a case study of Optimus being used with Flowmaster from Mentor Graphics. My name's Taylor Newell. I'll be joined by Doug Kolak from Mentor Graphics, and we'd like to welcome all of you. I do want to mention a few housekeeping items first. You all have been muted, so you shouldn't be able to hear any other sound from other sources, but you do have the ability to ask questions. There is a bar in the right-hand side of your screen where you can type in a question. I will handle some of those questions at the end. Those that will require a longer reply, or maybe a specific reply, we'll get back to you offline. In addition, this webinar will be made available probably within the next 2 or 3 days from our website, where you can go and download that to gain any more information about the process. We will start today. I'll give you a short introduction of Optimus and Oasis Solutions. Then I'll turn the time over to Doug. He'll introduce Mentor Graphics and Flowmaster, and also spend a little bit of time talking about the case study, or introducing the case study. At that point, I'll take it from there, and we'll discuss how the optimization was performed for this particular case study. And it's actually a very interesting case study where we made very significant gains in the efficiency of an aircraft HVAC system, and also made the environment much more comfortable for all of the passengers. So to begin introducing you to Optimus, we're a large company. We have over 2,000 installations with multiple 100+ user groups. You've all had interaction with customers of ours in the past. We have a worldwide distribution with offices in Tokyo, Shanghai, Munich, Paris, Moscow, Tel Aviv, Bangalore, Detroit, Indianapolis, and so forth. We're headquartered in Leuven, Belgium, where we have our development staff. Half of our engineering staff, some of our sales folks, are located there as well. As I mentioned, there's a good chance that you've had interaction with products that have been optimized by Optimus already. We're the most extensively deployed software of our kind. Primarily, we've been very popular in automotive and aerospace, although our largest growth is happening on the industrial side. Optimus is a process integration and design optimization software. It's typically referred to as a PIDO software. This allows you to intelligently run simulation-based design process to reduce the overall time that's required to run these processes, and give you more time for engineering decisions. And ultimately increasing the performance of a particular design. Optimus is a modular software, so you are able to select those modules that make the most sense for your application. We have a few of the modules that are listed below: process integration, design of experiments, optimization, surrogate modeling or meta modeling, and data mining. Robustness and reliability is another package that we don't have listed here. All of these modules together give you the ability to do just what we said before: reduce your design time and increase your design performance. The workflow inside of Optimus can be as simple as what you see on your screen here, where you have inputs, you define inputs that feed a simulation, and then you extract the outputs afterwards. Or they can be much more advanced, as some of our aerospace and automotive customers typically develop. Here you can see the interaction of a CAD model with a CFD model, an FEA model, and then post-processing on the far right. In addition to this, these of course can be captured as a sub-element inside of an even larger workflow. Optimus we give our users ultimately the ability to do multiple disciplinary optimization and workflows to utilize multiple CPUs and also to run all of these experiments or to run these workflows in parallel. So you can actually, from a single workstation, launch many different designs out over a scheduler, out into a queuing system. Really, the possibilities are limitless. It's a repeatable process that's also a robust process. So after the analyst that develops this workflow, for instance, moves on, it's very clear the process which he was utilizing. Not having worked on this product directly, I can tell you exactly what information is being passed to each of the different simulation software packages. So one of the first modules that we mentioned was the Design of Experiments module, and I'll talk more about this later. But the DOE module inside of Optimus allows the user to gain engineering insight into their designs. This is a great example. This was a 1D simulation that was being run on a poppet valve. What the user found by changing these four variables that are highlighted with these arrows, and they're listed over here, the hole diameter, the poppet half angle, and the duration that it's opened. What became very clear quickly was that for the three responses, the poppet half angle had almost no influence on the responses. The optimization problem could be reduced simply by removing the poppet half angle. Optimus allowed this user to rapidly identify the most influential design parameters, or perhaps in this case the least influential design parameter, and reduce the problem. Typically, after a design space has been identified and has been sampled, a response surface model can be generated. This is a mathematic approximation of an entire design space. And Optimus will generate essentially a mathematical formula so that now new experiments can be calculated on that mathematical formula instead of having to go back and forth to the simulation software. This allows you to solve new experiments very quickly. In addition to simply generating the response surface model, Optimus also gives the user information about the quality of that response surface model so that the user can select the best response surface model for each output. Optimus also has the ability to run single objective optimization. You see one example here where a user is optimizing a semi-cabin, attempting to minimize the drag on that cab. In this optimization, a design of experiments is conducted for the first 8 experiments, and after that, a gradient-based optimization is made. And you can see the improvements in the drag values throughout the optimization process. And I think here we got about a 10% improvement in drag. Now looking at that same problem as an multi-objective optimization problem, you'll see that drag was reduced, and at the same time volume was able to be increased on that cabin. At this point, a Pareto front is developed, and the user has the ability to select or to determine which parameter is most important. For instance, if volume was more important than drag, you would select a design on the right side of this curve. If drag was more important than volume, you would select somewhere on the bottom left part of this curve. But probably most likely you're going to select a trade-off, perhaps somewhere around this point on the curve. Optimus allows you to balance conflicting design objectives. And we apply many advanced optimization routines to allow you to do that. One of those optimization routines is specifically designed for robustness and reliability-based design optimization. And here, to give you an idea of what robustness and RBDO is, you'll notice that this gray point here is what's referred to as a deterministic optimum design. A design point that if we were to vary the input variable just a little bit, we would very quickly end up in the failure domain. Using the FORM or FOSM method inside of Optimus, we find a reliable optimum where the performance is not quite as good as the deterministic optimum, but if we make the same perturbation to the input variable, all of the responses lie in the safety domain. This, of course, is very important for design for Six Sigma and other RBDO problems. Optimus is a completely open platform. We have a full Python API where all of the functionality of the user interface can be accessed from this Python API. This, in addition to that, with a very small amount of programming, any user can add interfaces inside of Optimus. In addition to that, you have the ability to include your own optimization algorithms or optimization algorithms for codes that perhaps you're familiar with. Excel is an example where you can interface with the backend or with the optimization features of Optimus from a very familiar front end. In this case, you would be able to, or the user was able to distribute a workflow through Optimus to an entire design group by creating an Excel front end that was very easy to use. It controlled what parameters the designers were able to change, and then automatically created the workflow and ran the optimization. Optimus has the ability to, by default, I guess, or we have some installed packages with all of the popular commercial CAE simulation software, including what you see on the screen, but also many others. In addition, as I mentioned before, you can integrate with your internal software or other software packages that you have that Optimus may not have by default a interface for. Optimus has been used by many companies for a number of things. They're perhaps the three most recent that I'll mention here. Skoda Power used Optimus to find a 16% reduction in peak stress values on their steam turbine blades. It was used by an automotive OEM to increase the engine power by about 8%. And at Trane, Optimus increased the fatigue life of refrigerant lines on a new generation of chillers. They were able to greatly increase the number of experiments that they could run in the same amount of time. So at this point, I'll turn the time over to Doug. He'll give us an introduction to Mentor Graphics and the product that we'll be working with today, Flowmaster. So Doug, I'll turn the time over to you.
Thank you, Taylor. I'd like to take this opportunity to thank Noesis for allowing me to present here today. My name is Doug Kolak, and I'm a product manager for the Flowmaster product line at Mentor Graphics. I want to give you an introduction to Mentor Graphics, and more specifically, the Mechanical Analysis Division, as well as an overview of the Flowmaster product, which we will see more of later in the session. Mentor Graphics has been around for a little more than 30 years and is headquartered in Wilsonville, Oregon, which is just outside of Portland. Mentor Graphics is one of the leading companies for electronic design automation, but also has a focus on computational fluid dynamics and thermal tests. This is handled by the Mechanical Analysis Division, which Flowmaster is a part of. Flowmaster itself has been a product for around 26 years and was acquired by Mentor Graphics a few years ago. So why is simulation important to Flowmaster customers, in particular thermal fluid simulation? Risk is always a concern for companies, but usually as a project progresses, the risks associated with the project tend to decrease. One of the main driving factors behind this is the increase in information that happens during this progression. By gaining knowledge early in the process, companies can begin to lower the associated risk sooner. So this is where upfront CFD work can add significant value to the process. So normally we might have a first physical prototype once we get to a place where we're comfortable with the trade-off between risk and information. If we can look at using virtual prototypes earlier in the design process, we can actually shift some of this testing effort earlier where it's going to be much less expensive because we can do it using computer software and CFD versus building real physical prototypes. Because physical testing is time consuming and again, very expensive. So how do we help our customers handle these types of things? Well, in Mentor Graphics, Mechanical Analysis Division, some of our strategy is to enable companies to meet their business goals in today's competitive market by being able to differentiate their product. And they can do this through increased design, especially early in the design phase, keeping their development costs as low as possible, and being able to be first to market because they can do the simulation earlier and get it out faster. We believe that the best way to do this is through putting accurate and efficient analysis in the hands of not only the CFD specialists that can be involved late in the process, but also in the hands of the mechanical engineers, so it can be done earlier. We can do this by leveraging superior CFD core technologies, really in a wide range of different products that we offer. And let's take a look at some of those products. So what's the solution portfolio that we have to offer at Mentor Graphics? If you're looking at thermal analysis of electronic systems, Flowtherm is the market leader in the electronics vertical for computational fluid dynamics. If you're interested in looking at testing, hardware testing, thermal and optical, Tristor is one of the best options out on the market. If you're looking at heating and ventilation in buildings, Flowtherm enables you to optimize the airflow and temperature distributions in and around those buildings. In terms of a general CFD package, FlowEFD is the only fully embedded CFD program for the mechanical design environment. You have the option of looking at FlowEFD for CATIA, Pro-E, as well as Creo and NX. And finally, the one that we're looking to talk about here today is Flowmaster. And that's a 1D thermal fluid CFD package for really all industries that deal with fluid simulation. So what are some of the industries and usages of Flowmaster? Well, it is used across a wide range of industries. By far the most common are the aerospace, automotive, and power generation industries. From an aerospace perspective, the systems of fuel systems as well as the environmental control systems are a very popular option, and that's one of the example we'll be looking at today. From an automotive perspective, a leader in vehicle thermal management, so not only the cooling of the engine, but also the engine lubrication. In terms of marines, a lot of the safety systems and really any of the liquid systems on board. Same with oil and gas. A lot of the liquid pipeline systems are a very big strength for Flowmaster. In power gen, looking a lot at the cooling systems as well as some specialty systems on gas turbines and as well as our new two-phase steam capability for the steam systems in traditional fossil fuel power plants. We also look a lot at process, rail, and water in varying degrees. So what is Flowmaster actually used for by our customers? So it's described as a system-level thermofluid CFD tool, but what really is that? The focus is on fluid dynamics at a system level, so how different components will interact with each other on a fluid flow basis, as well as any thermal characteristics that need to be considered as well. By doing this, you can understand the pressures and the pressure drops in the system, temperatures of the fluids as it goes around, as well as the flow rates to ensure that you can meet what is required of your system, starting at the early phases of the design process, all the way through to the later stages where you're doing validation and verification. Flowmaster can be used for all of that. The way Flowmaster can help you do that is through, first off, the fact that any type of CFD program at the system level needs good loss data, loss coefficients. And Flowmaster is built on some of the most well-respected loss coefficients out there, the Internal Flow Systems book by D.S. Miller. You do have the option for both steady state and transient analysis, so it can look at sizing as well as how your system will actually operate. It can look at a large range of different types of fluids. So liquids, where we can look at it as an incompressible fluid, gases, including any compressibility effects that need to be accounted for, refrigerants, such as an automotive AC system or an aerospace vapor cycle system, and as I mentioned, two-phase steam for the steam systems in fossil fuel plants. In addition to just the standard steady state and transient, there's also a lot of specialty solvers to look at different types of applications, such as heat transfer, swirl in gas turbine engines, priming for engine lubrication, as well as flow balancing for easily sizing your systems. In addition to being able to meet the design requirements of the project, there's also the need to be able to work collaboratively and how you'd be able to manage all of the data and the information that's necessary to look at system level simulation. So since Flowmaster is actually built on a relational database to store all of this information, things such as components, performance data, the models, the results, any documents that are associated with it, it's very easy to have access from any user that you give the ability to access the database. There's also an audit trail functionality that tracks the changes that users make to the data for the different components and for the different design parameters. And you can actually easily compare that against previous versions that you may have created and roll back and decide what is the optimal design for moving forward. And with any type of relational database, you need to make sure you have a good ability to manage the users who have access to it, and Flowmaster has that implemented for use. And lastly, one of the key strengths of Flowmaster is being able to integrate it with other CAE codes. Companies are often interested in using best-in-class solutions, which means the ability to work between multiple programs. With Flowmaster, it's very easy to customize and extend Flowmaster to embed any intellectual property that you may have or in-house codes that have been used for years and could be then used with Flowmaster. Also, integrating with third-party tools, such as an optimization code, such as Optimist. That's how we went ahead and we worked on the project we're going to talk about today. And then beyond that, being able to co-simulate with other tools, things like a MATLAB Simulink, or being able to use a functional mock-up interface. These are all things that Flowmaster is able to support because of this openness and system integration. As a result, we have a large range of customers that we're able to deliver real business value to, whether it's working with a company like Mahle Powertrain in the automotive industry or an aerospace company such as Senior Aerospace. We know that customers are able to deliver improved design quicker than if they're not using a tool. So with that, before I pass it back to Taylor to discuss the project, I wanted to give a brief introduction to the model we're going to be using that he's going to be showing. What we wanted to do was optimize the behavior of an aircraft air distribution system to the cabin. And so what we've done is we've looked at the fresh air that's coming in off of the air cycle machines, and we're holding that at a constant value because we want to optimize for where that is at that particular design point. And what we want to do is we want to ensure that we have the appropriate pressure drop, so as minimal as possible, while not using piping that's overly large and going to add to weight of the aircraft. Looking at the fan size and the efficiency of it to ensure that with the energy that we're putting back into the system, we're not raising the temperature of the recycled air too high. And we also want to look at what effects having the gas bursts, either open or closed, is going to have on the system. Ultimately, we want to make sure that the cabin temperature is within a specific range that people are going to be comfortable with, as well as that the distribution of that temperature is as consistent as possible so that people at the back of the aircraft are getting as close as possible to the same temperature as people at the front of the aircraft so that really everybody can be happy with the cabin comfort. With that, I'd like to throw it back to Taylor.
Thank you for the introduction to Mentor Graphics, Flowmaster, and the case study that we'll be looking at today, Doug. At this point in our agenda, we will begin talking about the case study. We'll show a 1D thermofluid design optimization with Optimus and Flowmaster. I want to first establish or talk about a few items, though. As many of you realize, there's a very strong need for automation in our engineering work. It gives us the opportunity to spend less time on non-value-added tasks, scripting, file transfer, data transfer, things like that, and more time making engineering decisions. In addition, we realize if we look at the amount of time we have in a year, about 8,700 hours, that we're only spending about 2,000 hours, working hours in a year. Of those 2,000 hours, we may only be doing value-added tasks for about 1,500 hours. That leaves a substantial amount of time, over 7,000 hours, that could be utilized by automating tasks. This number grows dramatically if we were to run tasks in parallel. But there is a very significant productivity gain that we could access by automating repetitive tasks. And that will be a large part of what we will talk about today, how we can utilize some of that time. As we prepare to show you this case study, I'll use a few words that you may be familiar with or maybe not. A design of experiments, or a DOE, is a statistical population of a parametric design space. This DOE gives us the ability to learn about our design space, to give us insights perhaps into the design that weren't initially obvious. When we talk about optimization, we're referring to the concept of iterating design parameters to get a better performing design. An analysis will simply be, or is simply, a model that's solved in Flowmaster. And a surrogate is an alternative to a physics model that incorporates certain data. Typically, this data will be a response surface model, or an RSM. The RSM is a mathematical approach that delivers the surrogate model, and we will explain more about the RSM a little bit later. And finally, we will finish the case study with a very short discussion about reliability. When we refer to reliability, it's the ability of the system to perform well under small perturbations. Now, I want you to recognize, or hopefully you'll notice as we go through this case study, that when we combine Optimus with Flowmaster, there are really three very obvious benefits. The first is that Optimus with Flowmaster creates or enables workflows that are extremely easy to set up. You can take repeatable simulation tasks and very quickly automate them. This gives you the ability to change parameters such as dimensions, speed, etc. Very quickly. And it also allows you to integrate Flowmaster with other tools that are available. Flow EFD is one such example. When we combine Optimus with Flowmaster, we also see a very significant increase in speed. The amount of designs that we can solve in a given amount of time, and we will highlight how that happens in this case study. And we utilize some of that, some of the productivity gain that we talked about previously by enabling unattended parametric analysis. In addition, you can apply intelligent optimization methods that will iterate through the design space very quickly. And ultimately, when you combine Optimus with Flowmaster, you end up with a very flexible method. You can include in-house tools and processes. You can drive the entire workflow from the web or a Python environment. And you also have the ability to complete or conduct robustness and reliability assessments. Now, for this case study, the challenge is pretty simple. We've got a person or in a aircraft cabin, and we want to make sure that all of the people in the aircraft cabin have the same experience, the same temperature, or have the same temperature experience. We want to eliminate uncomfortable and inconsistent aircraft cabins. Ultimately, we want to maximize the efficiency of an aircraft air distribution system. And I want to point out something here, something that I learned or that Doug taught me as we were working on this project. These vents are actually referred to as gaspers. These gaspers, of course, are what allow individual passengers to regulate the temperature at their specific location. Doug mentioned a little bit about how airflow works inside of an aircraft cabin. There is typically an amount of free air or fresh air that's allowed into the cabin. Typically, this air is actually regulated. The percentage of air that comes into the cabin is regulated. For instance, an aircraft may be required to have, say, 5% fresh air or free air allowed into the cabin. That air is combined with recirculated air here at number 2, and this represents the recirculation fan that we will discuss today. The air is then pushed through a variety or a number of orifices or a number of pipes, I guess, that we will discuss, or will change the diameter of those pipes, and then the air is let out, of course, through the gaspers that we showed before. That air is then sucked by the recirculation fan back into the system. And so our objectives are ultimately to maximize the efficiency of the system. We found that the baseline configuration was extremely inefficient, as you'll see shortly. In addition to maximizing the efficiency, we want to keep the temperature between 18 and 24 C in the cabin. And ultimately, we want to keep the temperature as homogeneous as possible throughout the entire cabin. So we want to make sure that the passengers at the front of the cabin and the passengers at the rear of the cabin are experiencing the same temperature. So we want to minimize the deviation throughout the entire cabin. Here you can see the Flowmaster model that Doug created for this analysis. We begin, of course, in the top left with the recirculation fan. This will be an input parameter where we can adjust the speed, the fan speed, between 1,000 RPM to 4,000 RPM. Then we have 7 gaspers. The gasper openings can vary from 0 to 1, with 0 being fully closed and 1 being fully open. Then we also have 7 orifices that are identified throughout the length of the cabin or connected with each gasper. These orifices can have one of 3 sizes. It's either 1/2 inch, 1 inch, or 1.5 inches. And then finally, the response, or where we make the measurements, are at each of these 7 nodes that you can see here. These node temperatures must be between, or the constraint for these node temperatures is that they must be between 18 and 24 C. Now, as you saw, this is how our model is set up. We have 7 orifices. The values range between 1/2 inch and 1.5 inches. There's 3 separate values. We have gasper openings that can range from 0 to 1. They're stepped at 001. And we have a rotational speed for our fan from 1,000 RPM to 4,000 RPM. So that gives us a total of 15 input parameters. And then, as you saw, we have 7 responses. Now, we actually take the mean temperature value so that we're looking at one temperature, and then we also look at the deviation among all 7 temperatures, and also we calculate the efficiency, or we receive the efficiency that's calculated by Flowmaster. You'll notice this image a few times throughout the process, or excuse me, throughout the presentation. This is the optimization process that our customers typically work through. The first step is to capture the workflow. This is typically done inside of the Optimus user interface. After the workflow has been captured, a design of experiments can be created. As you'll see, the design of experiments is extremely easy to create. Usually with about 3 or 4 button clicks, the DOE can be created. After the design space has been sampled with the DOE, we're ready to create a response surface model. This is the surrogate model that we were talking about before. When the response surface model has been generated, a global optimization can take place very quickly on that response surface model. In fact, I believe in our case we ran about 5,000 experiments in about a second. After we've selected our optimum and validated it, we can then conduct a reliability optimization to ensure that we have a stable solution. So let's look at the first stage of this process, capturing the workflow. Here you can see the Optimus interface. You'll notice the workflow in the center of the screen. We begin with control parameters. Those parameters are defined on the left. This is where we specify the range for each of those each of the 15 input parameters. Then we have 3 icons in the middle that are responsible for creating the input file, launching and running Flowmaster, and then extracting the data from Flowmaster. And then to the right, we do our processing on the responses. So this is where we obtain the temperature information, calculate the mean temperature, calculate the variance, and so forth. We also have a few other items on this user interface that you'll notice. On the far left, you'll notice the post-processing options that the user has. Then in the tree, you'll notice the different methods that have been run. So for instance, a DOE has been applied to this workflow. Later on, an optimization was applied to the workflow. And down here, we ran a Monte Carlo simulation when we began to look at the reliability and the robustness. On the right side of the screen are the different interfaces which Optimus can work with. These, of course, are the interfaces which the user has already installed. Optimus has hundreds of software packages that it can interface with. And as you can see here, we only have maybe about 10 or 12 installed on this machine. At the top of the user interface, you'll notice a number of methods that can be selected. This would be a nominal method, so to run a single case, a design of experiments, an optimization, or Monte Carlo analysis. Then to the right, you see we have different models that can be created. So a Kriging model, a radial basis function model, or a number of additional user models, which include fuzzy logic, Gaussian distribution, etc. Or excuse me, a Gaussian response surface model. Optimus is designed to interface with each individual software in a very similar fashion. The user customizable interface that you see here will extract all of the parameters from the Flowmaster input file. As a user, you simply specify which Flowmaster file that you'd like to interact with, and Optimus will automatically extract all of the parameters. After you've selected your parameters, you simply add those to the workflow. After you've specified your input and output parameters, you're ready to place a user customizable action. This action gives the user a few options that they can select for running Flowmaster, and is then responsible for launching each individual instance of Flowmaster. So for instance, here you'll see the user has the option to select a steady state or a transient. They can identify the number of iterations or the maximum number of iterations that they'd like to run, and even include some owner and description information for the Flowmaster model. Now let's get into the baseline or the initial model that we have. You'll remember that we needed to keep our temperature at each of the locations between 18 and 24 C, and you'll notice that at the nominal condition, all of the temperatures violate that constraint. The mean temperature is well below the minimum required 18 C. The efficiency is at 0.355, so 36%. It's a very poor efficiency value, and the variance is extremely high. So taking that information, that nominal information, we're ready to begin our design of experiments. In the design of experiments, we're able to run the analysis at different points throughout the entire design space. The points are typically selected based on some statistical formulation. Of course, we have the factorial DOE and the 3-level full factorial, but there are other design of experiments configurations that may make more sense. For instance, you can see the random DOE covers much more of the design space than simply the factorial DOE. We typically find that for CAE problems, a Latin hypercube DOE satisfactorily covers the entire design space. We ran a DOE of 100 experiments. This took about 2 hours of simulation time. And what we found, and we'll focus on this a little bit later, is that there was a high correlation between the rotational speed and the temperatures, and the mean temperature. After we have our design space sufficiently sampled, we're ready to create a response surface model. For those of you who are familiar with Microsoft Excel, the Add Trendline feature, this is essentially a response surface model. We're fitting a mathematical formula to experiments. A response surface model does this in multi-dimensional space, and it can use more than just a least squares regression to calculate that model. In fact, Optimus has a tool which will go through and test about 20 different response surface models and select the best fitting response surface model for each of the outputs. In this situation, we found that the quadratic model was the most appropriate response surface model for the temperatures, and the radial basis function model was the most adequate for the efficiency calculation. The post-processing tools inside of Optimus give you the ability to gain more insight about your design space, or even about your response surface model. For instance, here we see, through an analysis of variance, that the rotational speed is responsible for 96% of the linear contribution to the mean temperature. This gives us quite a bit of information, of course, knowing that the rotational speed is the most sensitive. And when we do our reliability assessment, we will actually apply our variance, our standard deviation, our variance to the rotational speed in order to test the reliability. After we have the response surface model, we're ready to begin the optimization. We performed a global optimization with one objective function to increase the efficiency while using the mean temperature as our constraints. And of course, that mean temperature needed to be between 18 and 25 C. This was run on the response surface model, and what we found was that in 5,000 iterations, where we were able to complete 5,000 iterations in just a few seconds on that response surface model. Because we didn't have to call FlowMaster every time, we were simply calling a mathematical function. And here you can see the progress of the optimization. The color of the bubbles represents the iteration of the optimization. You'll notice that the original points were sampling the design space, and that very quickly we brought ourselves to satisfy the constraints, and then it pushed the efficiency up. And you'll notice, or you should notice, that there was a very significant improvement in the efficiency. In fact, we went from 36% efficiency to 89% efficiency, all while reducing our variance from 39 down to about 5, and of course satisfying the constraints that we were given. Now, very quickly, I just want to mention reliability. As we found out, the rotational speed of our fan was the most influencing characteristic on the mean or variable on the mean temperature. So in order to test the reliability of our optimal point, we applied a standard deviation to that rotational speed. You'll notice the bar chart in the upper left represents our standard or our distribution. We then ran 200 experiments, and we found that 44% of the time we ended up with a temperature that was outside of our constraint. That was unacceptable. So using methods inside of Optimus known as FORM and FOSM, we were able to run an optimization where we attempted to reduce the failure probability with that standard deviation. And this is the Pareto curve that we ended up with. You'll notice that our efficiencies weren't as high as we originally had with the deterministic optimization, but that with the robust optimization we have a selection where we can select a more robust solution. So finally, the impact of our optimization process. It took us 10 minutes to capture the workflow, 2 hours to run the initial design of experiments, about 5 minutes to automatically select the appropriate response surface models, and then just a few seconds to run the optimization. Then, if we wanted to find a reliable optimum, it took about an hour to run that FORM and FOSM optimization. Well, what we have is that in less than a day, we were able to run the entire optimization process. Now the impact of this hopefully is clear. We were able to increase the efficiency while satisfying the constraints. We were able to find a stable, optimal solution and automate this analysis. And this whole thing, this whole process was done in less than a day. And now we have something that's very repeatable that could be handed off to another analyst or to a designer, and they would get very similar results. In addition to everything that we've talked about, you also have the ability to import previous data into Optimus. So all of the Flowmaster runs that you've done in the past, you can actually import that data into Optimus and create these response surface models from that data. As you saw, you can run thousands of these simulations on that response surface model and even perform optimization tasks from data that you already have. Hopefully, as we've discussed this case study today, you've been able to see that when you combine Optimus with Flowmaster, it's very easy to set up. So it's very easy to combine Optimus with Flowmaster. In just a few minutes, you can capture your repeatable simulation workflows. It's fast. We were able to calculate thousands of designs in a short amount of time and then apply intelligent optimization methods that satisfied those constraints. And it's flexible. We were able to conduct a reliability assessment on our data after we had completed the optimization. We didn't have to start back from the beginning. So I think we have a little bit of time now. We can take any questions that there may have been. And if you'll give me a moment, I'll just flip through over on this other screen here. I'll flip through and find a few of the questions that we have. It looks like we do have a few. I'll take a few and then I'll pass a few over to Doug. The first question that I see is, how do you handle non-heterogeneous IT environments? Optimus can run on both Windows or Linux. Optimus makes no distinction where the simulation is taking place. In addition, Optimus will also handle the communication and the data transfer between those two platforms. We also have, with just a single button click, an interface with most, if not all, of the popular queuing and scheduling tools. The openness of the platform also allows you to connect with virtually any queuing or scheduling software or environment. There's another question here about the quality of the RSM surfaces. It says the most important fact of the response surface models is the quality. How do you make the decisions about the quality? So Optimus has a number of post-processing tools that allow you to gauge the quality of that response surface model. We give the user the R-squared values, the R2 press values, leave one out error, mean squared error, sum of the errors. So all of that information is provided to the user. In addition, we have a module which I showed which will automatically run a number of response surfaces and then select the most efficient or the most accurate response surface model for the output. So we can actually apply different response surface models to different outputs. And then, of course, there's the question about do you offer trials? And the answer is, of course. And if you have any questions, if you'd like to demo the software, send us an email at the email on the screen here, info@noasissolutions.com, and we'd be more than happy to help you out. Now it looks like there's a few questions for Doug here. Doug, the next question I think would be for you. Was there any heat transfer accounted for in the piping?
Okay, thank you, Taylor. In this particular example, no, we did not look in the piping specifically. Most of the heat transfer came through the people components that were in there and the fan component. So all the piping was done adiabatically. We do have the option to turn on several models of heat transfer in these pipes. So if you wanted to look at it from an isothermal perspective, or you wanted to actually calculate the heat flux that might go through the pipe from the fluids to the ambient or the ambient to the fluid. That's something we could do as sort of a next step in this type of model.
Excellent. And the next question, where did you get the data for the components in the model?
Okay, that was a good question because it came from a couple different places. I mentioned earlier in my overview of Flowmaster that a lot of the components come with built-in performance data, mainly pressure drop data for things like the bends or valves from the Internal Flow Systems book by D.S. Miller, a book of excellent performance data. In terms of some of the other areas like the people component, just to get an idea of how much heat would be put into the system, I've just kind of looked online what you could get. Also, ASHRAE has some really good data on something like that. In terms of the fan component, that was just from experience, some data that we've seen from some manufacturers, data that we've gathered over the years. And that's really how we see a lot of our users using Flowmaster as a combination of literature, manufacturers' data, and really as the models tend to progress, it's very easy to switch in more accurate data that you may get from your manufacturers of different parts.
And I guess along those same lines, and this is perhaps a question that I had, what level of detail are you able to model in terms of the temperature in the cabin and the passenger comfort?
Okay, so in that model we saw there were a couple points where we looked at the temperature, and so we just kind of said, here's the 6 or 7 points we're going to look at the bulk fluid temperature, because that's really what we're looking at. And this is an aircraft cabin, so it's a really big cylinder. We just kind of discretized it along the length and said this is the bulk temperature we're going to see. If we wanted more detail, we could always chop that up a little bit smaller, because I think we were looking at 2 rows per passenger component there, so about every 2 rows we were looking at. You could go to every row if you wanted to as well. If you wanted some more detail than that, so say you want like actual velocities that are going to hit the person and how that convective heat transfer may affect their comfort level, that'd be something where we might look more at a 3D tool like the FlowAFD tool we have to look at something like that. That's a little more than what Flowmaster does.
And finally, another question here is, are you able to look at transient behavior as well?
Absolutely. In this one, we were looking just to size the system, so pressure drops and temperature going in. So steady state absolutely sufficed for this. If we wanted to look, say, how the controls we might want to look at and how we balance the flow coming off the air cycle machine with the recycled air, that would be something where, yeah, we'd put some controls onto the system, and we could then run it in a transients analysis. So, yeah.
Excellent. Thank you very much, Doug. At this point, we will conclude our webinar. Thank you very much, Doug, for the work that you've put in, and I'd like to thank all of you for joining us. Please feel free to email either one of us, visit our websites to get more information about the product. Thank you all, and have a good day.
Thanks again, Taylor. Thanks, everybody.